Okay, so what just happened? Let's go over it step by step. We loaded and visualized our data. We edited our data to get into the right shape, as well as normalized the values between 0 and 1. We also edited our answers to be in a categorical form instead of a number, as our model will better train with that type of answer. We then created our model, compiled our model, and trained our model on the data. Let's start with our data. We received each 28 by 28 pixel image as an array of 784 integers. We then normalized that data by dividing it by 255, the max value for a pixel. Let's talk about our model. We can't fully represent it in a slide because it has many connections. Remember that there are 784 inputs, 2 layers of 512 neurons, and an output layer of 10 neurons, one for each digit. Every neuron in each layer is connected to every neuron in the next layer. With this, we have a lot of connections. 784 times 512, plus 512 times another 512, plus 512 times 10. Looking at this, can you guess what the approximate magnitude is? We have 668,672 connections. In order to understand how this network came about, let's look at a simpler model. Each of the circles on the slide before is a neuron. The earliest use case of this neuron was to build a regression line, good old y equals mx plus b. Regression is when we use an input to predict a continuous output, like using how many seconds a pot of water has been sitting on a stove to predict the temperature of the water. For each variable coming into our neuron, we're going to find a slope, or m. We'll also find our y-intercept, or b, which is a constant value not impacted by the other variables. Our goal is to find a line that could pass through these points. That way, we can use that line to make predictions. Some of you that have taken statistics before probably know of a more deterministic way to get m and b. We can verify through algebra that m is equal to 2 and b is equal to 1. We're going to do a more trial and error approach. We're going to pick random values to start, usually between -1 and 1. But we're going to pick 5 for m and -1 for b to make things easier to visualize. The y hat here, the one with the little hat, is going to be our estimate of the true value, y. Most of the time, our guess is going to be a bit off, so how do we correct it? Traditional regression lines are built on the concept of least squared error, meaning we're going to take the difference of each estimate from the true value and square it. This keeps the error positive, so when we figure out our total error, they don't cancel each other out. It also strongly punishes bad guesses. If it's been a while since seeing some of these math symbols, no problem. We can code our root mean squared error, or RMSE, like this. For each of our points, we'll figure out what the difference is between y and mx plus b. Then we'll square that difference, and then take the average of all the squared differences. Okay, phew, that was the mathiest we're going to get today. Let's graph out our m and our b in relation to our mean squared error. On the left, we have a surface plot of our loss function. That's the error function that we choose to evaluate our model, which in our case is the mean squared error. It's a little hard to read, so on the right, we've plotted the contours. With that, we can see it's actually a kind of parabolic ellipse that bottoms out at b is equal to 1 and m is equal to 2. If this is our guessed line, we can see where our current position is on the curve. Our goal is to find the minimum error, and since it's a toy example, we know that the minimum is 0. For us humans, it's easy to see that the bottom is around m is equal to 2 and b is equal to 1. But for the computer, it's not so easy to see that. The computer can't visualize the loss curve without some help. Turns out the computer isn't the best at calculus, so we're going to help it cheat. We have 2 levers to help us move, m and b. We can change b our intercept or m our slope. Let's start with b. If we subtract 1, cool, our line hits one of the points now. But it's still missing the other one. Let's increase the slope by 1. Darn it, now we're missing both points. But the MSE did decrease from 2.5 to 1. The computer doesn't have our human eyeball ability to guesstimate what it should change in order to get to the bottom of this bowl. So what it's going to do is, given the current position that it's at, it's going to calculate the gradient, which is a fancy way to describe a multivariate slope. It's going to figure out in which direction is the loss decreasing the most, which is going to be some ratio of b to m. Once we have a direction, we need to figure out how far to travel with it. The gradient is going to change depending on our current position, so we don't want to make too big of a step because we can accidentally move farther away from our target. We also don't want to be too small because that means it can take a long time to get to our goal, and life is too short to wait for our model to finish training. The amount we travel is something we decide, and it's in a parameter called the learning rate. Now that we're in a new position, we repeat the process, find the new gradient, and take another step. There's a few ways to measure our progress. There are epochs, which is another way to say one pass through all the data. It used to be that people calculated the gradient using the full data set, but nowadays people see that it is more efficient to use a sample or batch from the data set. In either case, a step is when we take either a full data set or a batch, calculate the gradient, and update our parameters with the gradient and learning rate. After a few steps, this is what our journey will look like. This process to find the minimum loss is called gradient descent. Thankfully, a lot of research has been done on the best way to define the learning rate, and machine learning frameworks have a few tools that will automatically adjust the learning rate for us. For instance, a popular one is ADAM, or adaptive momentum, which is kind of like thinking of our loss curve as a mountain and our position as a marble. If we drop a marble on top of a mountain, it will pick up speed, jumping over trenches, before hopefully landing on a lower minimum. Now that we have the core concepts down, we can start building up our network. Instead of having a singular x input with the slope m, we're going to have multiple x inputs, x1, x2, x3, and so on, and find each of them a weight. Our previous math stays mostly the same. We just need to find the gradient using the new variables like we did before. We can also take the output of one neuron and feed it into another, and as long as we don't make a loop, we can connect the same output to multiple inputs. Ba-dum! With this, we officially have a deep learning network. When we calculate our new weights from gradient descent, we can use the error calculated in a later neuron as part of the error for the previous neuron it's connected to. Most frameworks automate this part for us, so we're not going to go too much into the math. But I'll leave some links in the notes that explains how it works. There's one mathematical gotcha we should keep an eye out for, and that's our activation function. Right now we're just doing a linear sum, so we get a line in 2D or a plane in 3D. This is a bit of a waste on a neural network, since the only output we'll get from adding up lines together is another line, and it would be nice to be able to capture more complex shapes. Here's the strategy. Computers like equations of a line because they're quick to compute, and it's easy for us to give it the rules on how to differentiate them. One easy way to add nonlinearity is to feed our equation of a line into another nonlinear function. One of the most popular ones is ReLU, the rectified linear unit. This is just a fancy way of saying whenever the output of our line is negative, we're going to set it to 0. Because the output of our neuron gets assigned a weight if it's fed into another neuron, there's a chance the output will become negative. Another important activation function is sigmoid. It manipulates our lines so we get this S shape that goes from 0 to 1. This is great because then we can use our neurons to assign probabilities to predictions. All of these graphs start with a linear plane that gets squeezed through an activation function. In actuality, we're likely to have more than one input into our neuron, and this is the shape these activation functions give our neurons in three-dimensional space. Linear is just a plane, like a sheet of paper. ReLU is like a wedge, and sigmoid is like a surf wave. Here's how an understanding of all this math is going to help us. Let's say we have a one input, one output dataset, and we suspect it's a summation of two waves. We can use a sinusoidal activation function in our first layer and a linear activation in our last layer so we can add the two. Given enough data, our neural network will figure out the parameters of each of these subcomponents for us. Having a general understanding of the shape of the data and the relationship between the variables can help us build more efficient models for our data, saving time, computation, and ultimately, money. If we can make these complicated shapes with more and more layers and neurons, why not make a super big neural network to solve every problem? Can you think of any of the pitfalls that can happen from having too big of a model? We could be wasting a lot of computational resources, and it could also take longer to train. But there is another problem we should be aware of. The problem goes back to classical statistics, but it still plagues neural networks. Let's say we've gone out, collected some data, and created two models. Which one of these is better? Going by the root mean squared error, it's the one on the left. But what if I was to go out and get a new sample of data? It turns out our simpler model does a better job generalizing to new data. Not all problems can be so simple, and it's the job of the data scientist to be able to determine the correct complexity for the problem. Remember when we had two separate pools of data, training and validation, so that we can be sure the network is not just memorizing the data that it's learning on? We need to make sure that when it sees new and different images, that it is accurate as well. If the model performs well on training data, but not on new data, we call this overfitting. We just went over many parts of a neural network. Let's see how it applies to the last lab. This was the visualization of the model used in the previous lab. Can you name some of the components that we just learned on this diagram? Any details missing? Here's a more detailed version of the diagram, now including activation functions. We use ReLU in our hidden layer to add efficient nonlinearity, but why use sigmoid at the end? This way, we can get a probability for each digit. But wouldn't it be useful if all the probabilities for all 10 of our digits added up to 100%? How can we do that? Not a problem. There's a function many machine learning libraries have called softmax. It's going to add the results of all the sigmoid functions across the layer and then re-weight them so that they all add up to 100%. Let's say we have a group of points that are categorized by color. How will we use a root mean squared error line to predict whether a new data point is going to be red or blue? This time, we want to find a line that best separates the data. The error function that we use to calculate our gradient descent is called the loss function or cost function. We could try to assign numbers to these colors and use root mean squared error, but there's a better way. The most popular way to approach this problem is with categorical cross-entropy. Before we dive into the math, let's talk about the logic. We're going to assign a probability to each point whether it's red or blue. We could almost take this probability as our confidence it is a particular class. Cross-entropy was designed like this. If we are 100% confident that a point is blue, and we're right, perfect, we have zero loss. However, if we're wrong, we should be punished for our hubris and receive infinite loss. This works in the reverse case as well. If we assign a point a 0% chance of blue, that is, if we're absolutely certain it is red and it is not blue, we get no loss. However, if it is blue, we'll have infinite loss. Here's the full mathematical formula for binary cross-entropy, meaning we only have two classes. The logarithms are used to get our near infinite loss. It might seem like a lot, but there's a little trick. The left half cancels to 0 when the target is false, and the right half cancels to 0 when the target is true. Here's the code version for all you programmers out there. This is the same math as the slide before, but in code form. Y hat is our prediction that a point is blue, and Y actual is whether a point was actually blue or not. The logarithms are what will push our code to infinity, as log 0 is negative infinity. Okay, now that we know the major mechanics, let's talk about the next lab. We're going to try this again with a different data set, the American Sign Language alphabet. We'll have the same shape as last time, 28 by 28 pixels. We're going to be skipping J and Z because they require movement. Feeling more confident about neural networks? Let's get to it!